Oggi c'è più gente in poltrona.
Eh sì, forse l'ha detto. Good morning.
Buongiorno. Good morning.
La settimana con l'ufficiale.
Okay. You can hear me, I guess. I hope so. So, good morning, everybody. So we started. So we discussed some. We discussed some general issues last time regarding what we want to achieve overall in this lecture. So I explained to you that the particle flux to the target is determined essentially by the pressure of the plasma at the target. And the power flux to the target is essentially the product of the pressure of the plasma at the target times the square root of the temperature at the target. And in order to reduce the power load and the particle load, which is itself then relevant to erosion to the target, there are two ways. First of all, reducing the target temperature, so the temperature of the plasma in front of the target, because this also reduces the erosion. I mentioned that ideally, in an ideal world, you would have something like 2 to 5 electron volts in front of the target in order to minimize the erosion yield. And of course, it helps you to reduce the power load. And on top of this, to reduce the power load, you would like to reduce the pressure. And in order to reduce the temperature, we had this radiative dissipation that could be done, for example, by impurities. And for the reduction of pressure, you would have this momentum loss factor that was some value between 0 and 1. And I explained to you that in order to reduce momentum, there were 3 channels. One was perpendicular transport, which I didn't detail very much. One was charge exchange, so with neutrals or molecules. This spreads the pressure that you would have focused on one flux surface, would bring it further out and would make your profile broader. Reducing the peak is all you want. Or volumetric recombination, because it removes particle out of the system, transfers the momentum to neutrals, which are not bound by magnetic field, and thereby also spreads the pressure. So I then mentioned here that there are some uncertainties when we try to quantify impurity radiation. Yeah? So this is an issue. But there are also other aspects that one wants to look at. So when we think of the radiative losses that we have, so it's not written in here, but if we look at all the components that lead to radiation losses, so one is, for example, impurity. purity radiation, yeah. So I've listed these here, but there's also radiation or energy losses due to recycling fuel species. So in this figure, where I talk to you about these plasma wall interactions, you could see here, I hope you can see the error also online. So you could see here the plasma impacting, and then the fueling species come back as reflected particles or as recycled particles. And when we usually, I mean, to be very precise, reflection and recycled particles are both recycled particles. It's just we distinguish the reflected particles because they are essentially like a ping pong ball hitting a wall that just gets reflected, yeah. While the other is thermal diffusion. So these neutrals, they go back to the plasma, and then they eat up energy in the process of being ionized. And this energy that is used to reionize them is essentially the potential energy that you need to ionize a particle times the particle flux. But more precisely, because I told you last time, there's a step ladder-like ionization process. So neutrals are not instantaneously ionized. The electrons in the neutral is excited and then can decay or be re-excited again by electron collisions. This is a step-like process. And this means that the energy for ionization is a function of the temperature and is something between the minimum that you need, the absolute minimum that you need to reionize a recycled molecule is 15.5 electron volt. Why? Because it's 13.6 to ionize an atom, and it's about 2 electron volts roughly per atom to dissociate a molecule. So the total energy per dissociation is 4.5 electron volt, but if you then distribute this per atom, it's half of it. And this is where the 15.5 come from. So this is the absolute minimum from quantum mechanics. And this 50 or even to 100, for very low temperatures, goes even up to 80 or 100 electron volt, is because at temperatures of 2 eV, there's no instant, or there is very little instant ionization. Most of it is step ladder-like ionization. So if the temperature is 2 eV, tricky question maybe, does instant ionization exist? So can you provide ionization with one go using, let's say, 13.6 electron volts? So let's say the plasma temperature is 2 eV. I just explained to you that you have more processes of step-like ionization. My question is, are all the processes for ionization step-like ionization, or is there also direct ionization? So one single electron hits the neutral and immediately ionizes it if the temperature is 2 eV. Yes or no? Yes, and why? Correct. Yeah, because you have the Maxwellian energy distribution of the electrons. So there are always electrons that have more than 13.6 electron volt energy. Yeah, they always exist. Even at the most coldest temperature, yeah, of 1 Kelvin, yeah, there would always be an electron that's fast enough. It's just the amount is so low that this is negligible compared to the rest of the process. Okay. So when we try to think of the recycling of particles at the targets, things we are not so sure about is the relative role of atomic and molecular processes, because for this we would need to know in 2 dimensions in the diverter the distributions of the neutrons. So from a diagnostic perspective, so from an experimental perspective, it's very difficult to extract such an information. Yeah, just analyzing the plasma. we'll see later, we will have some numerical tools that can assist us in doing so, but just from an experimental perspective, it's nearly impossible to have this information by itself as such from a spectroscopic measurement. Nevertheless, you need the spectroscopic measurement, but you need tools to interpret them, and we'll get to these later. Another item that I have not discussed is what is called here the Lyman alpha opacity. So usually when the density of the atomic neutrals is very high. So first of all, when you have atomic neutrals, you'll always have Lyman alpha radiation, because that's the transition of an electron from the first excited state down to the ground state. Lyman alpha is in the ultraviolet range of the spectrum. So in order to detect it, you need spectrometers that, let's say, are more complex to maintain, are more intense for personnel resources or human resources, because you can't, so for example, ultraviolet spectroscopy doesn't work in air, because anytime the ray of light goes through air, this fraction of the spectrum is absorbed. And so you need to do this in vacuum. So the whole system of the spectrometer needs to be in vacuum. For example, on ASICS upgrade, for this reason, we don't have a system that observes these lines for the diverter. We have them for the core system of the plasma, but not in the diverter. On the other hand, at JET, such a system exists, and also in D3D. Okay? But we've never installed it because we don't have the human resources to do so, and it costs money and it costs a lot of time. However, when a Lyman alpha is emitted, you can imagine that if there's a neutral next door, neighboring neutral, that is cold, so that doesn't have a Doppler shift, or where the photon doesn't see a Doppler shift of the neutral moving away, then a Lyman alpha can be reabsorbed by a neutral, and thereby increase the probability for reionization of the atom, because then you don't only have electron collision, you also have Lyman alpha absorption. But how important this is something one can estimate a little bit back of the envelope, but the problem is that the density of the neutrals is not constant. So in a plasma where there's a lot of plasma, let's say, the amount of neutrals will decay because they are easily ionized, so the population density decreases. And in other areas, you'll have lots of neutrals, but there the emissivity is maybe lower because the electrons are then also lower. And so this role isn't so important. So there's every once in a while, there's a discussion in the fusion community if Lyman alpha absorption is important. And then the discussion always is it important for the overall particle balance? So for the power absorbed, for the particles ionized, or is it just important from a diagnostic perspective? So that when you look at spectroscopic data, for example, at Balmer lines, you need to take into account the fact that lower states, there's Lyman alpha absorption. So this is a discussion that always comes up, and I would say there has been some very good work at JET, from Bart Lomanovsky, because JET is a large device, so the mean free path, or the distance that a photon needs to fly to escape this neutral cloud, of course, plays a role. In a small machine, Lyman alpha absorption is nearly essentially irrelevant. For TCV, the densities of the plasmas are so low, so this is the tokamak in Switzerland, and the machine is so small, it doesn't matter. For ASICS upgrade, it's unclear, and for JET, it plays a role at least on the diagnostic side, maybe not for the overall particle balance. Okay, small excursion here. Then we have recombination. Recombination, as I told you, starts to play a role below 2.5 eV. There are different paths of recombination that I highlighted last time. One is this three-body recombination. At neglect here the radiative recombination because usually it's not so important. So you have this three-body recombination. So the reaction formula is written here. So three bodies because it's a ion. So H plus is symbolic for any hydrogen isotope. Yeah, so it's also true for deuterium or tritium, but in this context, it's always written hydrogen. And then you have the two electrons. So this is three-body because of momentum conservation, which gets down to one neutral atom and an electron. Now, when does this become important? So at temperatures below 2.5 electron volt, usually the reaction rate coefficient goes up. So the probability for this process to occur increases. But I also told you that when the plasma, when an ion flows to, always moves to the target. You can imagine that it takes a certain time for the ion to reach a target when it's in the diverter. There's a connection distance, so there's the connection line, the feed line, the ion travels along the feed line. It takes some time to reach the target plate. And if you have a probability for this three-body recombination to occur, this probability also can be translated into an average time that it takes for three bodies to recombine. And flying to the target is in competition with being recombined before hitting the target. So you can also look at the whole process as a competition between these two times. The time for volumetric recombination to occur and the time for the particle to hit the target. Okay? So even if the temperature is very low, in many devices, or in some devices, three-body recombination still may not play a role if the transient time of the ion across the plasma to hit the target is very short, because it hits the target much more likely than it will recombine despite the low temperature. So how can we increase the residence time of the ions? How can we slow down the ion to reach the target? Any ideas? What would slow down an ion that is freely flowing to the target? If you think of what I showed you in the past, you go back to this figure here, and there is this process here, the charge exchange process. So when it hits the neutral, I told you, you transfer kinetic energy to the neutral, which means you slow down the ion. So while charge exchange processes don't seem to be a major or a decisive channel to reduce the ion flux to the target as such a lot, yeah, they are though crucial for triggering the recombination process, because the recombination takes time. You need to slow down the plasma. You need to give the ions more time to recombine. Yeah? I mean, it's a very simple concept in the sense that if you slow them down so much that they would take infinite time to reach the target, then at any temperatures, all particles will always recombine before they hit the target. Yeah? So it's always a competition process, and the question is always which process is more dominant. And this is what the research often is about, to identify for this device, for these experimental conditions, is this a relevant process or not? Or if I do an experiment, am I doing an experiment that is relevant for a machine like ITER or DEMO? Can I approach the relevance? How do I need to change my plasma conditions so that I can reach a condition where things are not just interesting from a physics perspective to analyze, but are becoming of relevance for a device? And for this, I need to check what are the key underlying physics processes, and are these of relevance? Yeah? And they become of relevance when three-body recombination becomes of relevance, and this becomes relevant if charge exchange processes are relevant. So we can do, for example, a small numerical model where we play around, we switch off. In a model, we can always switch off processes or switch them on. and check. And what has been done in the past is to check, okay, if you switch off charge exchange, do you still have volumetric recombination? What turned out at the beginning when people started doing this, what turned out is they switched off charge exchange and they saw that suddenly the momentum loss, so this pressure loss, isn't so big anymore. And so sometimes they attributed it to the fact that they had just switched off the charge exchange process and said, oh, charge exchange process is the process that removes momentum. But that's not true. Yeah? Charge exchange is the process that triggers the loss of momentum by volumetric recombination. And this can only be understood when you look at the individual processes in detail and not just as a... So the details are often important. Then the other process that is contributing to recombination is what I explained to you last time, this molecular assisted recombination process. It's in this table, it's this process here. It's just condensed to a shorter formula here. Yeah? So this is the ionized molecule plus an electron that produces 2 hydrogen atoms. But in a fusion device, this is often in competition with this reionization process. And it's a very sensitive, depending on the availability of molecules and the temperature of the electrons. So it's a debate. It's definitely a process that plays a role, but it is expected that for a large device like ITER demo, this process here is dominant. Okay, so if we now look at the parallel heat flux that reaches the target, it is the parallel heat flux that we put in upstream, minus the power lost by recycling from neutrals that radiate in the process of being ionized, minus the amount of power that you lose from perpendicular transport, so for example, this turbulent transport, minus the power that you lose by recombination process, because that also costs energy, and of course, minus the impurity radiation. Yeah? So these are all the components that can reduce the power flux to the target. There's nothing else. Now the question is, what do we know? Or I told you last time that there is a minimum fraction of power that you need to dissipate. You remember there was this, how much power reaches the target compared to how much power is allowed to reach the target because of the components. Now the question, you can ask the other question, you can go to the physicists and now ask, okay, what is the radiation? Do we know anything about how much radiation we can actually achieve? Is there any model or equation that we can apply to estimate how much is the achievable radiative fraction? Can we look at it from this perspective? Can we check if these two numbers are compatible? Can we learn anything about the achievable radiation? And so, without deriving all of the equations, one can actually, has to be updated, the slide. So it's not anymore submitted. So this is published in 2019 or 20 in PPCF, a longer review paper by Peter Stangeby. And the equation I'm discussing here has also been originally published in an article also in PPCF by Spencer Pitcher and Peter Stangeby in 1999. So a long time ago. However, it's quite instructive. So if you use some simple analytic equations that describe the relation of an upstream location to the target pressure, that make some estimates on how much power you radiate from recycling or how much power you need to recycle neutrals, you can come up with a relationship that is written up here. So the fraction of radiation that we can achieve depends essentially from some function that we call K in this simplicity. and of the ratio of the upstream pressure to the power flux upstream. So this means your achievable radiation increases with increasing upstream pressure and decreases with increasing upstream power flux. Now, this may be, let's say, not so easy to understand. Why would this be? Can one explain this in more simple words? Why this would depend on these two things? Well, it is possible to do this. So upstream pressure, often, let's say, the upstream pressure, you remember in the introductory slide, the particle flux to the target is proportional to the upstream pressure, or the target pressure, and therefore the upstream pressure, divided by the square root of the temperature. So forget about the temperature, just it's somehow proportional to the target pressure and therefore to the upstream pressure. Why? Because there is density in there. The more density you have, the more you radiate. Yeah, this is essentially written here. Yeah, so radiation is some product of the square of density, more or less. So the product of electron density and impurity density. So the more density there is at the target or in the diverter, the more you will be radiating. So higher upstream pressure helps you to dissipate power. On the other hand, more power flux to the target usually leads to a hotter target. And a hotter target usually is unfavorable for radiation because you need a cold radiation for the recycling nitrides. Oops. Sorry. So, and then comes again here this momentum loss factor. You remember we had it before when we said we need to reduce the pressure. So the achievable radiation without any momentum loss would just depend on this relation and this weak function of target temperature, without going into the details of this equation. So if one looks at this black curve, this is for ITER, but actually this is for the old ITER that was conceived before 2000, which looking back is often called the large ITER, the ITER that never was going to be built because it was too expensive. So it has nothing to do, or not much to do, with the current ITER. That's a reduced version of this original ITER idea that Reagan and Gorbachev had, let's say, agreed on doing as a common project. So, so this ITER here, if there was no momentum loss, you would get this curve here. The fraction of radiation would be something around 60–70%. But you remember that for ITER we needed about 80%. So this would be here, and you can see there would be a gap. And so in order to increase the power loss, you need momentum loss. And if you increase the momentum loss, then you can even reach 100% of radiation. So again, everything falls on our feet, wondering how much momentum loss do we have? But as I explained to you just the last 15–20 minutes, momentum loss is very complex. Yeah? There's charge exchange processes. They only come in once you have impurity radiation. All this triggers volumetric recombination only if the temperature is low enough and only if the neutral density is high enough so that you have enough neutrals to slow down the flow of the plasma. So a lot of processes are coming. Okay, so let's assume we can achieve some radiation, then let's say the particle flux to the target is then governed by the, let's say, okay, there is something that limits the particle flux to the target. Let's start from this side. This is called the recycling flux. Yeah. So you remember that. Let's try to be a bit consistent here. So you remember that right at the beginning, we had particle flux to the target was proportional to the pressure at the target times or divided by the square root of the temperature. And the power flux to the target is essentially the pressure times the square root. You can also write the power flux to the target as the particle flux to the target times the square root of the temperature. Yeah, I mean, for this P, you could write gamma. So the power flux to the target will depend on how many particles reach your target. Okay. So, but if you radiate a lot of power upstream, at some point, the question is, how much particle flux can you actually sustain still at the target? Because if you radiate a lot of power, let's assume you have a region where a lot of impurities are, and they radiate power. Yeah? At some point, you have reduced the power to such levels that, let's say, if you have the recycling process going on, but each cycle of ions reaching the target and coming back eats up energy. Yeah. So in order to sustain this recycling process, you need a certain amount of power. And this amount of power is, in its most simple way, the potential energy for ionization, or if you're more sophisticated, this ionization energy here, yeah, times the particle flux. That's the power you need to sustain the power. And you put in power upstream, and assuming you have no perpendicular transport, just radiation, then this will be balanced. So once you radiate by impurities so much power, you may come down to a point where the particle flux that you can sustain is limited. And this means you are essentially, we call this power starvation. So once you have enough radiation, the recycling flux is limited by the available power to sustain the recycling flux. This is another way of saying why you need a lot of dissipation of energy. Because the more you dissipate, you go into a regime where at some point you don't have enough power to sustain the particle flux that you could sustain due to the plasma pressure upstream. So, but this power starvation at the end of the day actually is only possible if you have removed pressure, without going into the details here. But this type of equation, so in a simple analytic world, you enter a solution of this analytic formula once the temperature is below this critical temperature here that is depicted. Where's my arrow? There. This critical temperature that's below 5 to 10 ED. So this formula here has some bifurcation when you plot it. And this bifurcation, there's a lower temperature branch of this formula, which leads to this expression here. So for low temperatures, once you have reached these low temperatures, the particle flux to the target is limited by how much power you have radiated. But you can only reach these low temperatures if you have radiated enough power and dissipated enough power. And you can only dissipate enough power if you have removed pressure. Okay? So it's a bit of a usually not easy to digest concept. Okay, so this all seems very complicated at the end of the day. And this analytical model that I've even reduced drastically is, let's say, the most you can do analytically. It doesn't tell you anything about the individual processes that are important or the discharge conditions that you need to set in. It's just a guideline. This is a very abstract concept that just serves in this context here to provide some mental guideline to get some order in this vast processes that are available. Yeah? So just to, in German we say, to see the forest despite all the trees. Yeah? So this is the idea. So because everything is so terribly complex, we need at the end of the day to analyze the things. You need to have some numerical simulations that take into account all these processes. Okay, so this makes the need of numerical simulations. And now we come to a word that I haven't even used so far. And this is diverter detachment. So we talk about diverter detachment, or the process of diverter detachment, so detaching the plasma from the target, is by our definition the loss of pressure. So when you have sufficient loss of pressure between the upstream location and the target, we talk about detachment. Yeah? So this is what we call detachment. Often in the literature, detachment has been used just when the power is reduced. Yeah? But this is true for an operating device nowadays. But for a future device like ITER and DEMO, the reduction of power is not achievable without loss of pressure for all the reasons that I've just explained. But because the parallel heat flux to the target is proportional to the pressure at the target times the square root of the temperature, for current devices, so machines like TCD, or even to some extent, if there's not too much heating power in R6 upgrade, you can reduce the power flux to the target below, let's say, critical levels for the components just by reducing the temperature without reducing the pressure. But for ITER and DEMO, this is not possible. You need the reduction of pressure because of this curve here. Yeah? Because otherwise you can't reach the high dissipation levels. You need pressure loss. Even if you radiate like hell, without pressure loss, first of all, you can't radiate like hell. And secondly, you will never reach the dissipation requirement, this minimum required dissipation that we had in the simple formula before. Okay, so what else do we know? When did we start? 1:45? So should maybe have a break in 15 minutes or so. Yeah. So what relationships do you need at hand to guide yourself in this forest? So first of all, the total pressure that I've always been talking about is the static pressure times the kinetic pressure. The CS is this ion sound speed that I introduced in some earlier slide. And so without pressure loss, the pressure at the target is equal to the pressure upstream. Yeah. And then we have the further assumption that the electron temperature is equal to the ion temperature, even though I told you yesterday in everyday life this is not true. Yeah. But for simplicity, we assume this. So there's something called the two-point model that essentially assumes that the target temperature is lower than the upstream temperature, that recycling magically occurs somehow without being forced to take into account the energy losses from the recycling. So recycling is happening in this model, but this power limitation on how much you can recycle isn't taken into account in this simplified two-point model. So this is why if we use this two-point model that's based on pressure conservation and the, let's say, the Spitzer-Herm power flux to the target, if you take these two assumptions and you assume that the plasma flows with Mach speed, so with sound speed to the target, then you can come up with these relationships. So you can find a relationship for the upstream pressure, upstream temperature, which tells you that the upstream temperature is proportional to the parallel power flux upstream to the 2/7. Now this parallel power flux upstream to the 2/7, this parallel power flux, we said is the power entering the scraper layer, so P sol divided by some surface area, which depends on the decay length lambda cube. So essentially it depends on P sol. But this tells you what? That the upstream temperature of a scraper layer plasma is essentially given by the power and is a very weak function of the power entering the scraper layer, because the exponent is 2/7. So even if you double the power, the variation of the upstream temperature is very small. So upstream temperature is roughly, that's why often when you work in this field, many people assume that in H mode, the temperature of a tokamak like jet is roughly 100 eV, nearly always. Why do they say this? Because for how much they vary the power into the scraper layer, this value doesn't change very much. Of course, if you look into the details, this generalized statement is not true. Yeah? If you look into the details, then you see, okay, the temperature upstream is something between 70 and 130 eV, and it doesn't matter on the discharge conditions what temperature you have. But for the sake of simplicity, often they say, okay, it's just 100 eV because of this weak dependence on the power into the scraper layer. The target temperature depends, of course, on the parallel upstream heat flux, the connection length now. Why on the connection length? Because Spitzer Herm was something that was temperature to some high exponent times the gradient of temperature. And the gradient of temperature is the gradient along the field line. And the field line length is the connection length. So this is where the connection length comes in. And then it depends, has a strong inverse dependency on the upstream density, which means this formula here tells you if my plasma density is low, my target will be hot. Yeah? If my density is high, if I have high upstream density, my target temperature will be low. This is what these relationships tell you. That's why I put in just the proportionality factor, not the equation of this two-point model, because you shouldn't take these two-point model things for the sacred holy grail. They're just a guideline to get a feeling for how, let's assume I could double the temperature, the density upstream, then this would tell you, okay, this would reduce my temperature at the target by a factor 4, roughly. Yeah? In reality, it will not reduce by a factor 4. It will reduce strongly. Yeah? Maybe a factor 3, maybe a factor 5, maybe a factor 6, depends on what other multitude of processes kicks in. The target temperature, the target density essentially is proportional to the cube of the upstream density. What does this mean for recombination? This means high density upstream, so also high plasma pressure, is beneficial to trigger recombination processes because the target density, which is important because it's a 3-body recombination process, so it depends a lot on the density of the ion and the electrons, goes with the factor cube of the upstream density. Plus the target temperature goes with the square, so it's inversely proportional to the upstream density. So increasing upstream density is beneficial to reduce temperature and to increase the probability of recombination because of having more particles and because of temperature. So it's always beneficial to operate at high density. This is what it's saying. And the particle flux to the target is also proportional to the upstream density. So the more you increase the upstream density, the more your recycling process will increase and the more you may be eroding your target, which is the negative side. So this is why you need to reduce it. Take this two-point model just as a guideline along these lines of thought. Do not take this two-point model as anything. Don't make experiments based on the two-point model. Yeah? Then we have these loss factors. I've introduced 2 loss factors. The radiative loss factors that here now has a bit different name, power loss factor. The momentum loss factor, which was the pressure loss. And then there's one more, which is conv. This is the convection loss factor. It's not really a loss factor. It's just a term that tells, okay, in theory, we assume all the power is conducted. But now you have ions reaching the target, the neutrals start, they leave the target, they will be ionized somewhere in the volume, and then they need to travel back, and they start forming a convective cell, or an advective cell, let's say, rather than a convective cell, an advective cell, where plasma flows to the target. And as soon as plasma flows to the target, heat is convected. Yeah? So some part of the heat that we assume is conducted, in reality is actually convected. And in order to take into account how much of the power is convected, one introduces this convective loss term. And you can see that these are all corrections. So you can reduce the particle flux to the target, if we just look at this, by increasing the momentum loss. So if momentum loss is 1, this thing here is 0, the particle flux is 0. So this just tells you what I've told you 10 times before. Momentum loss reduces particle flux. But also a higher fraction of convective transport will limit the particle flux. Yeah, if all power was convected, this would also reduce the particle flux to 0, which is a bit of a contradiction, yeah? Because particle flux is, but this is because of these limitations that are not in this model. This model is very oversimplified. So only take this model, let's say, not an extreme asymptotic behavior, but just as a guideline. Yeah. Why? Because if you radiate power, what is this telling you? If you radiate power, the particle flux goes up. Why does the particle flux go up if you radiate power? Because the density goes up, the temperature goes down, but because particle flux is density times square root of temperature, because the ion sound speed is a function of the square root of temperature, the particle flux the density goes up faster than the square root of the temperature goes down, because the product of density and temperature is pressure, and that's constant in this, if you don't have F momentum loss. Yeah? So this is why, but of course, you can bring this equation to a breakdown by saying, okay, all of the power is radiated, then this value is infinity. Yeah? We all know it cannot be infinity because recycling needs energy. So this value can't go, with a rational mind, this can't go to infinity. It can go to some limited value, but not infinity. This is why two-point model is good as a guideline, but it breaks down at several places. Yeah? So don't take it too seriously. Okay, of course, there are the questions that are outlined here. So what is the maximum value of the power loss that we can achieve? How much convection do we have? What is the maximum momentum loss factor? So do we observe this often talked about pressure loss in experiments? These are experimental data from CMOD measured by a diagnostic called Langmuir probes at the target and measured by a diagnostic that is able to measure the electron density and the electron temperature at the upstream location. And what is done here is put in the ratio of the target to the upstream static electron pressure. No information about the dynamic, just the static. We don't know if the upstream dynamic pressure is big or not. But implicitly, it's assumed that the upstream dynamic pressure is negligible. This is because we imagine that the plasma flows, that there's some stagnation point upstream, where the plasma flow velocity is very low, close to 0. It's not true, but it's the assumption. At least it doesn't contribute very much to the total pressure. So what you see here is the function of the target to the upstream static electron pressure as a function of the target electron temperature. Why is it plotted over the temperature? Because I told you all these charge exchange recombination processes, they kick in at low temperature. And this is what you can see here. Essentially, for temperatures above 10 electron volt, there is no pressure loss seen in experiment, as we would have expected from everything I told you so far. Yeah. But at low temperatures, you see that this curve is decreasing. This means that pressure is lost because the target pressure compared to the upstream pressure is reduced. Yeah? So here at around 2 eV up to a factor 10, and as you go down, you can see the pressure loss is stronger and stronger. And you can intuitively imagine why this is, because at these temperatures, I told you, when the density is high enough, you start triggering volumetric recombination. So it's very likely that in this area here, the reason why this curve looks like this is likely because there's volumetric recombination and likely some charge exchange process taking place. This is just a curve to show you pressure loss exists. It's no miracle. And there is a threshold for detachment between 5 and 10 eV. Inversely said, when the experimental physicist that runs an experiment sees a plasma that is cold of 5 to 10 eV, then he says, okay, this plasma is detached or will detach, because our everyday experience tells us any time when plasmas have these low temperatures, pressure loss is observed in experiment. We have similar data from A6 upgrade. They look very similar to this curve. Yeah? There's no database for jet like this, but the data would exist to make such a plot. Okay. So then the other question is, can we achieve these 5 megawatt per square meter in current days experiments? Is this possible? So experiments have been done, and what does this mean for, let's say, I'm not very good at graphics, so this is a very artistic drawing. So what you see here is an area called the core, where all the fusion processes would take place. Then we have a region, let's call it the edge region. So it's the edge of the core. So it's the boundary of the core. Then you have this black line, that's the separatrix, and you have this magenta area, that's the scrape layer and the diverter. So can we achieve, let me just move this like this. So can we achieve the radiation requirements that we want, or the dissipation requirements that we want, and where should this occur? Obviously, in order to radiate, we do not want to radiate, or we want to minimize the radiation inside the core area, because that's where the fusion processes take place, and we don't want to cool down the plasma where the fusion takes place. We will need to radiate in the edge region, and we must radiate in the scrape layer region. Yeah. So the total power that we need to dissipate inside the last closed flux surface, the estimate is, in a machine like demo, is of the order of 60 to 75%. So 60 to 75% of the power need to be radiated inside the last closed flux surface in a reactor like demo, but ideally not in the core. Why? Because the scrape layer can handle only a certain amount of power. Where did I tell you this? I told you this. Sorry, I told you this here. The achievable radiation in the scrape layer is limited. It's limited by how much pressure we can lose. And because demo is of a, so the rationale is a bit like this. Because demo is of similar size to ITER, the diverter will be of similar performance to ITER. The ITER diverter is already, let's say, more or less at the maximum that one assumes one can achieve with the diverter. So this tells us how much power in absolute numbers one can radiate in the diverter. And if you assume this, then there's a certain amount of power that's left over that you need to radiate somewhere else. And then you come in with radiating inside the last closed flux surface. Yeah? So you would need to radiate 60 to 70%. So in order to achieve these overall dissipation that I told you last time of 90 to 97%, this means that 70% of the power need to be radiated somewhere here in the edge. Yeah. This is not fully true because, let's say, probably 20% of this power actually radiated in the core by Bremsstrahlung and synchrotron radiation that are God-given at a certain density and temperature of the plasma. So, how does this look like in the experiment? So here you see on the left the reference for a case of ASICS upgrade without seeding, and on the right with seeding. And what you see here are the corners of the tiles that are mounted to the target. And you can see in the left case, they start to glow because they receive so much heat. And in the right case, we have introduced nitrogen as a radiator and everything is fine. This just demonstrates the impurity seeding does do its job in a device like ASICS upgrade. If we look now in the colloidal plane and try to understand where is this radiation taking place, in the left figure is the case that was previously also in the left with the hot tiles. And the hot tiles we were looking at were the tiles here in the outer diverter. And you can see there's some radiation here in the inner diverter volume. There's tiny bit of radiation in the outer diverter, and that's it. When we do a lot of nitrogen radiation, then you can see that in this case that I showed you, a lot of radiation here is around what we call the X point. Yeah? And this dissipated the power so that the tiles wouldn't heat up, that they would produce these, what we often call these leading edges, this bright spots of radiation. One can do volumetric. This is now a case, for example, for JET. Previously, we had a ASICS upgrade. So at JET, for example, something very similar is seen without, in this case, neon seeding. You have this radiation here. And with neon seeding, you can produce this X-point radiator, which can remove, apparently, a lot of power from inside the last closed flux surface, but still in the edge of the plasma. So the requirement of this radiating in this red region is fulfilled in the experiments. So this idea of radiating this way in current experiments can be achieved. What we do not know is if this is extrapolable to a machine like demo. Check the time. Okay, I think we should do a break until 20 to 12 now. Okay. Wrong mouse. Okay, so we have now in these examples here introduced nitrogen in order to dissipate power. And we look, first of all, does it do what we want? And what do we observe in such conditions? So what is plotted here is what has been observed in an experiment that we did during a PhD thesis of a student of mine. So we puffed nitrogen from a valve that's located below this dome that I mentioned to you. So this is the inner target, the outer target. The blue line is the separatrix density. These gray lines, they're all lines of sight of spectroscopic of spectrometers. So we are able to select these lines of sight, and then usually they're collected here with a lens, and then with optical fiber they leave the machine, they go through the torus hall, they enter another chamber where there are lots of spectrometers sitting on tables, and then they're distributed among these spectrometers, and one can look at certain lines of sight. So what has been done here is these lines of sight that you see here, they've been used to send them to one spectrometer to evaluate, for example, the electron density. I don't know if I have an example of how this is done. Yes, I have. One is done for the nitrogen. So you look at specific nitrogen lines that are characteristic for, so wavelengths that are characteristics for nitrogen, where you don't expect any other impurity or any other molecule to interfere, so that you're sure you're looking at nitrogen and not fluorine or oxygen or tungsten. Yeah? You need to be sure the wavelength is well chosen. Otherwise, if your spectrometer doesn't have a high enough resolution or you selected the wrong wavelength, then you may have two neighboring lines of two different species, and you may be looking at the wrong thing. Yeah. So that's why you need to be careful. And then one can look at Balmer radiation in general. But when we talk about Balmer radiation, this means radiation from hydrogenic species in the Balmer lines. So you will know from basic physics what Balmer lines are. So there's the transition 3-2 of excited hydrogenic species. So as we introduce nitrogen, what one observes is, so in red is where you see high electron density. In blue is where you see Balmer radiation from hydrogen. And in green is where you see nitrogen radiation. And as you increase the amount of nitrogen, in this case, you see the movement of the Balmer radiation and the movement of the electron density from locations close to the target plate. So at low nitrogen seeding or no nitrogen seeding, the radiation and the high density are at here the inner target and here the outer target. And as you increase the nitrogen radiation, first you see the movement of the electron density to the export area. And then later you see the radiation, the movement of the Balmer radiation to this export area. And at the same time, you see that the region where the nitrogen radiates moves slightly inward. Yeah? There's a small shift inward. What do we end up with? We end up with a plasma. When we see Balmer radiation here, this means that neutrals are being ionized inside the last closed flux surface, which is an indication that the temperature must be of the order of 10 electron volts or below, because otherwise they wouldn't have the chance. If the temperature is very hot, you don't get a very high radiation, because you don't need this step-like ionization process anymore. It's just instantaneous ionization does the job, and then it doesn't emit very much light, because for emitting light, you need to have an electron transition from a higher level to a lower level. If this doesn't happen because you instantaneously ionize, the probability for seeing Balmer light is low. So the fact that you have a lot of Balmer light here is an indication that ionization is occurring in this volume. Okay, if this is the case, then this means low temperatures are observed here. And in fact, from spectroscopic measurements, our estimate is that we can cool down this area to values of 10·5 to eV. We're not sure. So if we look at the lines of sight and how do we measure density? So when I talked to you in the previous slide about electron density, how do we measure the electron density? Well, it's done in this case by spectroscopic emission. And what do we look at? We look at the delta epsilon line. So there's the epsilon line of the Balmer series. So there's Balmer alpha, beta, gamma, delta, and epsilon. And you see this is around 397 nanometers of wavelength. So it's a high resolution spectrometer. You see here oxygen line, a helium line that contaminates the delta epsilon line. So if there was a lot of helium in this plasma, then this information of the delta epsilon may be distorted if we don't know how much helium there is, because it would contribute to this line. And we have further oxygen lines. So what is done? You know the Stark broadening process for spectroscopic transition. If an atom is in an area of a larger electric field, you get a degeneration of the transition. Yeah, so usually you have a clear energy level for each transition. But if there's a strong electric field around the atom, then the transition doesn't get any more so clear. It becomes you have an uncertainty in the energy level that comes from the electric field outside. And this means, an uncertainty means a broadening of the profile. This is what you see here. So instead of having a very sharp peak that may go down like this, you get a broadening of the peak. And the broadening of the peak is proportional, or is a functional dependence of the electric field. And this itself is a functional dependence of the electron density. And so by measuring the broadening of this line, we can deduce what the electron density is on average along this line. And if we know where a lot of light is emitted, which we can do by looking at where these lines of sight intersect. So if we know that this line is seeing light and this one is seeing light, then we know the emission must be coming from here and not from here. Yeah, this is how we do it. Because otherwise you measure line integrated. You need to deconvolute this somehow by logic. And so in this case, this line of sight observed a density of 4 times 10 to the 20 per cubic meter. To give you an example, derived from the widening of this profile. So on A6 upgrade, experiments have been done. So this is now a typical time trace of such plasma experiments in tokamak. So this is the period of time of the discharge. So this discharge lasted 5 seconds. So you see here what we call time traces. Usually they're grouped in similar categories of values that have similar units or where you can normalize to something similar. So the top box is the heating power. So don't forget, so in these types of plasma, there's no power from fusion. It's just additional heating. So heating from human-made outside heating. So the heating power you see here is ramped up in steps. This is the black curve. Usually this is neutral beam injection. And then one can also look at the radiation. So you can see the radiation in the diverter increases. The radiation in the main chamber, so above the X point, increases even more strongly than the radiation in the diverter. And the total radiation is nearly as high as the total heating power, but you can see you can reach a very high fraction of radiation. So in this case, it's about 80% of the heating power was radiated by impurities. Then forget about this blue curve, just look at the black one. So this, sorry, the red one, this number here, H98, for the mortal plasma physicist, is a measure of how good the plasma is confined. So when you have an H98 of 1, this means it's a good confinement. And you can see that despite the radiation increase, the confinement is decreasing a little bit, but marginal. Maybe about 5% reduction in confinement, but not more, which means that despite adding all this radiation, the confinement is well maintained, which means the energy confinement is good, which means you're not deteriorating your core plasma. And at the same time, one can look at the heat flux that reaches the target. This is, for example, done by infrared cameras that look at the target tiles, and then one infers what the heat flux would be from the emissivity of the tile, which is infrared emissivity. And you can see that on average, so this is the 5 megawatt per square meter line, on average, the value stays below. So despite having 23 megawatt of heating power, which back then was the majority of heating power that was achievable, the power reaching the target could be left below 5 megawatt per square meter. Maybe you remember yesterday I showed you at A6 upgrade, ITER and demo, how much heating power and what this meant as a power flux. So there was something like A6 upgrade could reach 40 megawatt per square meter, and now at the total heating power, and here we reach less than 5, which means we are able to demonstrate in today's experiment that you can dissipate a lot of power. So I told you about detachment, and there are different detachment regimes. This notion is very qualitative. There's no very clean definition for it. And so there is a conceptual picture that shows this is approximately the position of the separatrix where it hits the target. And this is a concept of the profile of the heat flux along the target tile. So this, what color is this? Ochre sand color thing is the heat flux at the midplane, so upstream. So this is just an exponential curve. It's an exponentially decaying curve. And at the target, because heat also diffuses in the radial direction, In attached conditions, so no plasma pressure, essentially you have a profile that follows more or less this midplane heat flux profile. And in what we call partial detachment means that only one part of the heat flux is mitigated, the peak heat flux, while in the fast grip of layers, so from here on, it essentially follows the midplane heat flux profile. And this is the operational regime that we expect in ITER. So loss of heat flux close to the strike line, which is the main purpose, and then essentially normal heat flux in the fast grip of layer. And in a device like demo, we're aiming at this red or even this violet curve, yeah, which we call pronounced or full detachment. There is a semantic dispute, not a serious dispute, but some dispute of calling it pronounced or complete. Yeah? One can argue about this. There are two different families, let's say, of people that like to use. But essentially, the point is that you get these very flat profiles, yeah, that are essentially detached all over the place. They are disconnected, let's say, from this midplane heat flux profile. That's when you have very strong detachment, which you could also call it, yeah, instead of pronounced or fully detached. So this is the world of the what we call ITER-like diverter concept. So a single null diverter, so one magnetic null point. But what if it doesn't work? What if this concept of a single null diverter doesn't work? Well, then some people have come up with a concept of what is called the snowflake diverter. It's called snowflake diverter because it looks a little bit like a snowflake when you look at the magnetic equilibrium. And the idea is that there is some magical process that redistributes power among now not 2 targets, but up to 4 targets. And by doing so, if you distribute the power to more targets, you increase the wetted area, so the area where the plasma is in contact with the components, and thereby you reduce the heat flux per component or per square meter. Yeah? So this is the basic concept. So on R6 upgrade, we usually operate in the lower diverter. So no, these figures shall not say that R6 upgrade is the machine for what we call alternative diverter configurations. They are called alternative because they're alternative to the standard mainstream ITER-like diverter. That's why they're called alternative. Some people like to call them advanced diverter configurations, but I think they should only be called advanced once it has been proven that it has an advantage compared to the standard. So I personally, and a lot in my group, they also prefer to call them alternative for the moment. So we have here the standard ITER-like diverter in R6 upgrade. So these are the plasma-facing components here in gray. And these are just the equilibrium with different flux values in different colors. So don't worry about the color, they're just for illustration. This is the lower signal diverter, but in R6 upgrade, in the upper diverter, we are going to have a major opening in the near future to remodel the upper diverter to allow R6 upgrade to start experiments on alternative diverter configurations, which R6 upgrade so far can't do because of the colloidal coil configurations. It doesn't allow to do alternative diverter configurations in the lower diverter. Other machines like TCV or D3D or NSTX, they could already investigate alternative diverter configurations with their coil systems. R6 upgrade can't. But because we have a lot of smart people, they've come up with a new concept where you modify the target shapes here. You introduce here this red and green thing, colloidal field coils that go around in the toroidal direction that can run current, and they can modify the colloidal field. And this blue box here is a new cryogenic pump that's going to be introduced in order to be able, when we operate with the upper diverter, to have some control on the particle throughput by being able to pump at the top. So you can see here the coil support structure, the new target support plate, which will be water cooled, and the two counter current coils that are there. So this is just a schematic of the cryo pump that's going to be introduced and its specification. So what is the volume that it can pump at normal ambient temperature? So that's 65 cubic meter per second. So when the coil currents in these two additional coils is 0 kiloampere, then you can run a standard single null diverter. Yeah? So will be compatible to compare with the single null diverters. And in a single null diverter, this is just a concept, you would have something like this one here as a heat flux profile. From pure analytic things, it's something like folding of a exponential decay and some cutoff towards what we call the flux region. So I won't go into the details. So usually we have that this profile shape here is something like an exponential, and the width of this heat flux is 1 over lambda cube. Then because the plasma naturally diffuses radially outward, yeah, so essentially the plasma will diffuse into this direction here, outward, and also into this direction here. So this profile here, imagine turned around. So this area here is here, this area here is here, yeah, and this straight line position here is roughly here where the blue line is. Yeah. And because the plasma diffuses inward and outward, at the end, along the target, you get this type of a profile. Yeah. And so this is an attached condition because there is no real loss in the peak power flux. And this is what it would look like in a single null diverter. Okay. The idea is to show what happens in alternative diverter configurations. So if you manage to spread more power outward and into the flux region, then the peak will be reduced and the profile will become broader. Yeah? The total power under this curve is still the same as under the red curve as under the green curve. So the integral value is the same, but the peak heat flux has been reduced due to dissipation. In this case, dissipation by transport. And so on. And this is the so-called S parameter, which is a notion of the competition between perpendicular and parallel transport, assuming no other dissipation. It's just, this whole thing here is just about the concept of perpendicular to parallel competition in a single null diverter. So this has been derived in the past. So I'll just go now to the X diverter. So the X diverter is a concept where there is a second null point here, which is behind the position where the field lines intersect the target. Yeah, this is the X diverter. And the consequence is that the impact angle along this target plate is very shallow. So the red cross is where the second X point is. And under such conditions, because of the shallow angle, what we start having is that the perpendicular particle flux, so up here you have the parallel particle flux, yeah? And here you have the projection of the parallel particle flux onto the tile, which is the perpendicular particle flux. And in the single null case, you will have something that resembles very much the parallel particle flux in the shape, because it's just one fixed angle more or less along the target. But in the X diverter, you have very shallow angles, and the result of these shallow angles is that you get a strong reduction of the perpendicular heat flux. So the parallel heat flux is the same, roughly, is what this is saying. But the advantage through the X diverter would be that purely from geometry, you would be reducing the heat flux by a factor 5 to 10. Yeah? But this requires very shallow angles. Yeah? So I'll skip this. The problem with the shallow angles, I mentioned this yesterday a little bit. I don't want to go into too many details. You'll have the slides to look at them in more detail. What I want to tell you is that in normal diverters, what is done is you can't build a diverter made of one piece. At least most of the people think you can't. Maybe you can, but most think you can't because of if you have thermal heat load, there will be expansion of the material, and this will cause too much stress on the component. So what is often done is you break up this one diverter that you have in your head into smaller pieces, into smaller tiles. And now you need to align each tile next to each other. So in the ideal world, you'd say, okay, in the ideal world, I can make, let's say, 3 plates, each one ideally next to each other at infinite precision. Then you could have 3 flat plates sitting next to each other, but there will be a gap. And the feed line will come in at an angle. And if you have a gap, the feed line could hit the corner of the neighboring tile, but then it's not hitting it at a shallow angle, it's hitting it perpendicular. And then the perpendicular heat flux on this corner is similar to the parallel heat flux. And you remember I showed you this image of the seeding, non-seeding video, and you saw these edges lighting up. This is an effect of the gap between tiles. Yeah? But on R6 upgrade, as on many other devices, in order to minimize this effect, one has this inclination of the tiles. So now you have the plasma coming in from here at this impact angle. And then in order to overcome, let's say, the issue of the gap, so to avoid that the heat flux hits this gap, you make this fishtail-like process so that you shadow these areas. Yeah? So no heat flux can hit these corners here at a very steep angle. What is the price to pay? Well, the price to pay is that usually you would have all this here as wetted area, yeah, all of the target. But because you have now inclined the target, you lose this part here. Yeah, because it's not wetted by plasma. So as you do this process, you reduce the wetted area. The price you pay by reducing the wetted area is that the heat flux per square meter goes up again. But it's a fine balance, and this fine balance is this fraction of total wetted area as a function of these 2 angles and of these width of these blocks and the size of the gaps. Yeah, so this formula is just pure geometry. And then comes an additional part, which is this red box here. Now, of course, nobody on the planet can align these tiles to infinite precision. There will always be misalignment. And the question is, what is your tolerance? What is the maximum allowable tolerance that you would provide? And this is depicted by this delta psi. Yeah? And if you take all into this account, then you can play around with what the effect is of having very shallow angles to very steep angles, and how this impacts the tolerance you can have in the vertical position or in the gap size. So if you want very shallow angles, then this one becomes smaller and smaller. So this is the problem of the X diverter, especially because it lives off these very shallow angles, and so it introduces this complication when you work with this type of monoblocks. The result is then on R6 upgrade, they've decided to put in just one big tile, not single blocks, to avoid this problem of asymmetry. The consequence is that it can handle less power, but from the calculation in the experimental environment, still enough power to do meaningful experiments. Now one can also do something called a snowflake. In this, topologically, the snowflake and the X diverter are the same, but the difference between the snowflake and the X diverter is that this X point here now moves into the plasma, and you start to have 1, 2, 3, 4 intersections with the target. So you have now 4 targets, and the idea is that somehow this X point redistributes power to this, this, and this. But you can also already see that the likelihood for power reaching this target will be lower because you need to cross here and go here, or you need to do 2 crossings. And don't forget, parallel transport is always more efficient than perpendicular transport. But maybe with some luck, you could redistribute at least power that would go to this target, to this one and this one. Maybe not to this one, but at least to these 2 targets. So there's some hope that you can reduce the power. And if you just take geometrical considerations and you make a simplified world, then you remember upstream, so this is a parallel heat flux upstream that reaches the target. If now you look at the perpendicular heat flux, or the, doesn't matter actually, but if you would look at the perpendicular heat flux in the diverter, then in single null, we have this, this blue curve here. But if we could distribute the power to 2 more targets, then we would have this red and this orange curve. So red for this target, orange for this target. And one can, from simple geometrical assumptions, assuming that the diffusion across the field lines is in single null similar to snowflake, that the physics process hasn't changed, then you can come up with such redistribution of the heat, which shows that the peak flux could be reduced just from geometrical perspective. And this is what makes these alternative diverter configurations so attractive, because you can reduce the power just from a geometrical perspective. This doesn't tell you if any seeding is as efficient in alternative geometries or works as well. The point here is that the gain by distributing it in a snowflake diverter is smaller than 2, which means if you just have 2 targets, you would say, okay, I distributed, then my peak flux is just divided by 2. But the gain from the snowflake is that it's reduced even more than this factor 2, from geometry. Okay, I will skip this, and I'll skip this, and I'll come to the numerical tools. So we have about 15 minutes, so I'll start with the numerical tools because I think we stop at 12:30. Okay, numerical tools. So I told you everything is very complex, so we need a numerical tool to describe it, and a numerical tool is always never better than the model assumptions you make. It's reducing the world to some simplified concept that is never equal to the reality. So we do it, what is done is that this Landau's equation, imagine you have an ensemble of many, many particles. So we're talking now about many particle physics. And what this does, what this shows is the temporal evolution of the distribution function of this many particle system as a function of the position, velocity, and time, or temporal timestamp of any of the particles that compose this system. So this equation here at first doesn't have any assumption on what type of distribution I have. The distribution function can be whatever you wish. So, so you have the temporal evolution of the distribution function that will be, so this is, let's say, the movement of the distribution function in space and time, and its divergence of the distribution function in space and time. And all this will be balanced by collisions, which can be among all the particles of this system. So that's what's written here. Now one starts to make some assumptions. First of all, that we have a Maxwellian distribution. that we can assign a temperature. Yeah? This is an important assumption. So we assume that the plasma has a temperature. We can define a temperature. This is not necessarily the case. You should, when you have such a model and you say, okay, I can assign a temperature, then you need to do, is this really true? Can I really assign a temperature to this distribution function? Is it a good enough assumption that I can make? And once you've done all these considerations, you can then start to build up moments. So moments means you are making, let's see the slide, that you start to convolute moments of velocity. So you multiply your function with velocity, the 0th moment of the velocity, the first moment of the velocity, and the second moment of the velocity. So the 0th moment will give you the particle conservation equation. So this is the particle content. The first moment will give you the momentum conservation, and the second moment will give you the energy conservation, because it's v to the 0, v to the 1, v to the squared. So yeah, so v to the 0 is just particles, v to the 1 is like mass times velocity, and mass times velocity squared is energy. This is how you can, let's say, imagine it. So particle conservation, you must have seen such an equation before. So this is the temporal evolution of the density times the divergence of the product of density times velocity is equal to sources or sinks. Yeah, this number here can be positive or negative. Same for the electrons. It's a similar equation, just that you have particle sources and sinks for electrons. Then for the total momentum, you have this evolution of the momentum, the divergence of the momentum, and then here you have the gradient of the pressure. And because you can have several directions where momentum is evolution, you get something like a pressure tensor. Yeah? So it's a tensor product. And then you have the J cross B. J is the plasma current, B is the magnetic field, and sources and sinks of momentum. Yeah, why this? Because this can cause redistribution of momentum into a current and a field function. So the total current is defined here. And then the friction is, of course, important. So electrons and ions will have friction. And this here, the parallel and the perpendicular plasma current come in with a parallel and perpendicular electrical conductivity of the plasma. Because of the magnetic field, the conductivity can be different in the two directions. Okay, so, and then this one here is, because in the parallel direction, one always develops electrical fields as a function of the electron temperature. So this creates a force usually, and this force can accelerate the plasma that ultimately ends up of the plasma being accelerated to sound speed or more when it's in the proximity of the target. This is what this one here essentially is introducing. Okay, so there's a particle conservation equation, a momentum conservation equation, and then ultimately there's this energy conservation equation, once for the ions, that's a bit more complex, and once for the electrons. And again, you have here the sources and sinks. And then here you have the heat exchange between electrons and ions, between ions and electrons, and here between electrons and ions. Of course, this number in absolute value is the same as this one, because it's just how much these two fluids exchange energy with each other. These are the basic equations, and the whole thing is what we call closed via the heat flux. And for the heat flux, we implicitly make the assumption that the heat flux can be described by Spitzer-Ham. So this Spitzer-Ham equation that I showed to you before essentially is what is described here. without going into the detail, the complexity of the equations here is just for completeness, not for simplified understanding. Yeah. So the simplified understanding is that you have a Landau equation, you assume Maxwellian distribution, you derive the momentums of higher orders, you stop at the order of the energy equation, and you close the functions at the next, which would have been the next order, which would be the heat flux. But you do this by making an implicit assumption on the nature of the heat flux, saying, okay, heat flux is conductive heat flux. We assume, therefore, that the collisionality of the plasma is high enough that you can assume that heat is conducted by collisions. Yeah? This is the intrinsic assumption that one makes to close these equations. One needs to test if this is actually true or not. Yeah? So this means that the equations are limited to collisional plasmas. When the density of the plasma is so low that the probability for two particles to collide with each other is lower than for one particle reaching the target, then the assumption of this equation breaks down, and you can't apply a code that contains this assumption to those conditions. And this is something that you always need to take into account when you apply a code. Is the applicability of the code valid or not? Yeah, many people just apply codes blindly. They don't even think about if it's even valid to apply the code that contains a certain model. So these are the basic equations that are in this fluid model description that will describe the evolution of the plasma in space and time in the stratosphere. Then we have magnetic equilibrium. This is an example for the magnetic equilibrium of jet. And out of this, one produces a computational grid. Yeah, so one uses EFIT is just a procedure, but it's an equilibrium that has this, the gradient of the pressure is J cross B. So this gives you flux surfaces essentially of constant pressure. This is what it's saying here. So this equation tells you that each flux surface has its own pressure. Yeah. And then, of course, the rod B is produces a current. So these equilibria, or equation for equilibria, can be translated into a grid, which is a discretized description of this magnetic flux surfaces. And this grid is aligned with the magnetic flux surface. This is a principle of this type of a grid. There are other codes and computational processes nowadays that don't need anymore the alignment of the grid. But the grid in the past, these codes is more than 30 years old. And at that time, due to the computational requirements, because of the strong competition between the very fast parallel process and the slow perpendicular process, it was decided for numerical reasons to align the grid with the magnetic field in order to distinguish these two directions more easily numerically. So, but of course, reality is not as simple. Yeah, usually things are not, oops, should be a video here. So this is a cut design of the jet torus. So it shows you that the structures around are not two dimensions. So the fact that we are simplifying this to two dimension is a simplification one needs to be aware of. The question is this an acceptable simplification or not? Does it will alter my solutions, of course, but is the impact of these structures 5%, 20%, or 50% on my numerical solutions once I run the code? So you need to be aware and be able to estimate what the impact of it. Or is the phenomenon I'm looking at something where the walls play a role, or something where the walls don't really play a role? Then I don't need to care about the interaction with the walls. So also depending on the physics question that you want to address, you need to think, okay, is this applicable or not? Am I pushing the code to its boundary? Is this something I should do or shouldn't do? Okay, let's get out. Of course, one can also have three-dimensional. So reality is actually three-dimensional. It's just a reminder. So you can have one-dimensional codes, for example, in the radial direction or in the parallel direction. You can have two-dimensional codes, which is the workhorse that we usually use. Or we can have three dimensions. Of course, the more dimensions you take into consideration, the less sophisticated maybe your model is that you can use, because the numerical, let's say, the numerical power that you need increases with the amount of equations that you need to solve in more and more dimensions. Yeah? So also there, some questions may be sufficient to use a one-dimensional code. For example, some considerations you may want to do on turbulent processes. Maybe it's good just to use them in the radial direction. It will provide you some insight into the nature of the turbulence. Some others, if you evolve and have more computational power, you may do it in 2 dimensions or even in 3 dimensions. Yeah? But it will take you more time to reach an answer. So the codes will be slower. So usually what we do is we have a coupling of 2 codes. On one hand, for the scraper layer, we have 2 or 3 dimensional fluid transport code that solve these equations that I showed you before, these transport equations. So the equation for particle conservation, momentum conservation, and energy conservation. And there are various codes that are mostly, so UH is an American code, H2D is a code mostly developed at JET, B2.5 is a code that is developed originally, let's say, in Garching, and now more and more maintained in, well, Garching, Jülich, and at ITER. Solder is a Japanese code. EMC3 is a fluid transport code version that has been developed in order to be able to describe a machine like a stellarator that's intrinsically 3D. And SolH2D is a code that started as PhD projects with a different approach in France. Yeah? And these codes, I would say, B2.5, SolH2D, and H2D are containing more or less similar physics. The difference is EMC3 is 3-dimensional, so it contains the physics of 3 dimensions. And it doesn't need to be aligned with a numerical grid. What you see here is a solution of the electron density simulated with EMC3 ARENA for ASICS upgrade in 3D. Yeah? You see here some structures that are non-toroidally symmetric, and they come from some additional magnetic coils that one can take into account. For example, you can introduce into a device some coils that produce radial electric fields that are toroidally inhomogenic in order to study or impact transport in the perpendicular direction of the machine. But if you then want to model what does the scraper layer look like, because you break the toroidal symmetry, you need to have a code that can deal with this broken toroidal symmetry. And this is EMC3. And so this is something, a code that is also used in my group. But of course, you can also simulate with it purely toroidally symmetric, and you can compare how one code performs compared to the other. Maybe for the question one has, it's sufficient. And then these fluid transport codes that solve the plasma equations, they are coupled to neutral transport codes that are, because the neutrals don't follow the magnetic field, they need to be treated a little bit different. There are some areas where you could treat the neutrals like a fluid because the collisionality is very high, but there are other areas where you need to have a kinetic treatment because the plasma density is very low or the neutral density is very low. And so you need to follow neutrals as a ballistic object. And this is done by a Monte Carlo method following the Markov chain of events. So each event, so for example, each charge exchange process, elastic or inelastic, would be a random process where the computer rolls a dice, extracts a random number, compares this random number with the probability for an event to take place or not, and then decides which path to follow. Yeah. So this is, I think this is it. We should stop here, and then I can use this figure to start and pick up where we were last time. So I do not know, I didn't even give anybody the chance to ask questions. Are there any questions? No, I devastated you today.
Just,
I will stop or pause.
yes, just one
Stop.
stop. Just I mean.
See?